Okay, so we are going to start with the lecture. So what was the last definition which we were discussing in our lecture was Wronskian. Means I will give you this definition of Wronskian. Before defining Wronskian, we were discussing linearly dependent, right? Linearly independent or linearly dependent. So I'll just quickly recall you what do we mean by linearly dependent. So two functions, we were calling them two functions f and g, they are functions of x. We were calling them LD or linearly dependent if one can be written as the constant multiple of other. That means if you take their ratio fx by gx, that turns out to be a constant, right? Otherwise, if the ratio does not turns out to be constant, so we call them linearly independent. So LD is the word for linearly dependent, Li is the word for linearly independent, because in short we will be calling them linearly dependent LD or Li. So this is very easy to check. And now I'm going to give you another way, which is the Wronskian. This is a definition which I'll define. So this is another way to check LD or Li, because although in the context of differential equations, in many of the questions we will have two functions to check LD and LD. When I'll make a connection of this linearly dependence with the differential equation, then you will understand where we will need it. But right now I'm telling you that in the context of differential equations, most of the times we will need to check two functions. So it's very easy to check two functions just by this definition. You just take the ratio. If ratio turns out to be constant, then we say they are LD, otherwise Li. But this Wronskian is a general technique to check Li or LD. So with the help of Wronskian, you can check any number of functions, given 3 functions, 2 functions, 4 functions, any number of functions if you are given, you can check using the Wronskian to identify whether they are Li or LD. So that becomes useful there. And even for 2 functions, that is useful. So now I'll define what is Wronskian and then we will use it in the question. So Wronskian is nothing but it's the determinant of a matrix, right? Let me give you first the definition of the Wronskian for two functions. So it's denoted by W. So if you have two functions, fx and gx, you want to find their Wronskian, then what will you be finding? You construct a matrix. In the first row of the matrix, you write the two functions, and in the second row of the matrix, you write their respective derivatives, because they are functions of one variable, so they will have the full derivative, right? So fga, f dash, g dash. And then you take the determinant of that matrix. Remember, this is the sign for the determinant. So you form a matrix, the row contains the functions, the second row contains the first order derivatives, and then you just find the determinant. So this is obviously, if there are two functions, so Wronskian is going to be determinant of a 2 cross 2 matrix, right? And similarly, say I can give you definition it for 3 functions. Say you have 3 functions f, g, h. Obviously 3 of them are functions of the same variable. So then in the first row you write the 3 functions, in the second row you write their first order derivative, and then in the third row, because we are finding the determinant, so it's going to be a square matrix, right? So in the third row, what we are writing is f double dash x, g double dash x, h double dash x. So the third row will be containing their second order derivatives. So for 3 functions, you want to define the Wronskian, it is going to be a 3 cross 3 matrix, right? I hope you just get the definition, that how the Wronskian is defined. Once you're clear about the definition, then I will connect it with LD or Li, that what is that result where Wronskian is used to identify linearly dependent or independent. So it's easy. So you can construct a Wronskian for n number of functions. It will have it will be the determinant of a n cross n matrix, where the very first row is just the function itself, or you can say the 0th order derivative. The second row is the first order derivative. The third row is the second order derivative. Depending upon what is the order of the matrix, you will construct it like that. So once you are able to construct the Wronskian for given number of functions, then you can use this result to identify that whether the given number of functions are linearly dependent or independent. So I'm giving you the result that if y1 and y2. So now I'm giving you the result in the context of differential equations, right? So now we'll make a connection with the differential equations. So if y1 and y2 are any two solutions of homogeneous differential equation on an interval AB. So homogeneous differential equation, everybody knows that we are talking about here the second order solution, second order general linear differential equation of this type. Let me recall you. This was the type we introduced in the last lecture. So if this Rx happens to be 0, so this is a homogeneous differential equation of second order. So suppose for the homogeneous differential equation, we have the two solutions. These are two particular solutions. Then y1 and y2, obviously actually they are y1x, y2x, don't get confused that they are numbers, they are functions. Then y1 and y2 are linearly dependent if and only if Wronskian of y1 y2 is 0 on AB. Actually the word used is identically 0, right? So the Wronskian will be 0. So let's just look at each and every term very carefully. So y1, y2 are two particular solutions. So we are clear about the meaning of the particular solution. We are clear about the meaning of homogeneous differential equation. So why this particular interval is given to you? Because before this, we were never talking about the interval. So after this point onwards, you can say it is always a part actually of the differential equation, because whenever you say any solution, whenever you give any particular solution, it is going to have a domain of itself. Like I'll give you an example. Say, suppose some differential equation is having this as its solution. Suppose there exists a differential equation which is having one of its solution is 1 by x. Then 1 by x is obviously defined for all intervals except the intervals containing 0, because at x equals to 0 this solution is not defined. So the solutions, because they are functions, so they have some domains, they are not defined everywhere. So that's why the concept of interval is there, that the solutions are defined on some intervals AB, right? Then over that particular interval they are said to be linearly dependent if and only if the Wronskian is 0. So I hope the meaning of this is also clear to everyone. If and only if means it's true both sided, that if LD is there, means if the functions are LD, this will imply the Wronskian is 0, and if Wronskian is 0, this will imply the functions are LD. So this is a both sided result. Now let's come to what do you mean by identically 0. Identically 0 means the answer should be a constant, and that constant should be 0. The answer cannot be a function of x. You cannot have, say, just for example, the Wronskian turns out to be x, and then you say, okay, x can be 0. That means you cannot say for x equals to 0, the Wronskian is turning out to be 0. It's not going to happen, right? It's identically in 0 on the complete interval. It cannot be 0 on a particular point. Okay, so if that is happening, then you will say the functions are linearly dependent. We'll do examples and then it will put more clarification to the same. So this is the result which is connecting three things: Wronskian with linearly dependent functions, and then what is the connection of LD with the solutions. Okay, I'll give you one more result and then we'll do the examples. If anybody has any doubt till so far, then please ask. You can write your questions in the chat box. Okay, identically 0 concept means over the whole interval it should be 0. That whatever interval they are talking about, whatever values of x you are looking for, there it is completely 0. It will not be selectively 0 at specific points, right? Over the complete interval it is 0. It's not, the answer cannot be a function of x and then you figure out for what values of x it is 0, right? That part will come later, but right now this is the meaning of identically 0. LD is also 0. Nahi, don't get confused with LD. LD, let me write it more precisely. y1 and y2. See, what is our aim? Our aim is to know whether two given solutions of a differential equation are dependent or independent. This is our main aim. So suppose we have the two solutions and I want to check whether they're dependent or independent. So what I'll simply do, I'll compute their Wronskian. How I'll compute the Wronskian? Using this formulas for two functions. So if the value of this determinant turns out to be 0, I will say linearly dependent. If it turns out to be non-zero, I will say linearly independent. As simple as that. You compute the Wronskian. If Wronskian is 0, you say LD. LD means y1 and y2 are LD, linearly dependent. Otherwise, if Wronskian is non-zero, that will imply the two functions y1 and y2 are linearly independent. Right? So that is the meaning of this result. So now let me give you one more result here. Yes, okay, you just hold on for the Wronskian definition. I'll use that again in the questions. So if somebody has missed the definition of the Wronskian, I'll use that in the question, then you can see. So this is the next result, which says that if y1 and y2 are two particular solutions of homogeneous differential equation and are linearly independent. Suppose there are two solutions and are linearly independent, both of them, y1 and y2 are Li. That means their Wronskian is turning out to be non-zero. Then the general solution is y is equal to c1 y1 plus c2 y2. So this is the main result actually which we are going to use in the question, that if from two particular solutions you figure out the general solution, right? Otherwise, we know the reverse is always possible. If we know the general solution for any differential equation, we can compute the particular solutions. But this is the, you can say, remarkable result which tells you that if you know two particular solutions and they happen to be linearly independent, then you can always write the general solution as the linear combination of those two solutions, right? But suppose they do not happen to be linearly independent, like say, suppose y1 is x, y2 is 2x. Suppose these are the solutions of some particular differential equation, homogeneous second order differential equation. Then if you say c1x plus c2 times 2x, this is not going to be a general solution. Why this is not going to be a general solution? You can see from here, c1 plus 2c2 into x. X can be taken common, and what I am left with, c1 plus 2c2. And c1 plus 2c2 will be just another constant, right? C1 plus 2C2 is just a constant because C1 is one constant, C2 is another constant. So this combination is another constant. So this acts as a solution, but this cannot be the general solution. Now, please, can somebody tell me why this cannot be the general solution of a second order differential equation? Why this y is equal to c times x cannot be the general solution of a second order differential equation? Can anybody tell me that? Yes, because there has to be two constants of integration. There has to be two arbitrary constants. That's the first definition of general solution. That general solution, a particular expression, you name it as a general solution if it contains as many arbitrary constants as the order of the differential equation. No doubt it will be a solution. You put it into the differential equation, it will satisfy, but it is not the general solution, right? It does not contain two arbitrary constants, it just contains one arbitrary constant. So this is not a general solution. So this is the problem which you will find, that I give you two solutions of a linear differential equation of second order. If they happen to be, now which type I assumed? LD, because one of them was constant multiple of other. If they happen to be LD, then taking their linear combination is not going to give me the general solution. This is what exactly this result is saying, that if you give me two particular solutions and they happen to be Li, linearly independent, only then their linear combination which you construct is going to be the general solution, right? So this result we are going to use to find the general solutions of a second order differential equation. That you are not, it's not enough to have just two solutions. It is enough to have two solutions which are li. If they are li, then we are only going to use it. So this is the main result, and that's why all this theory was told to you. To check li, we need to know the meaning of ld, and mathematically, what is the formula of checking ld or li? That is this Wronskian. That is, you compute the Wronskian. If it is 0, ld. If it is non-zero, li. As simple as that. So I'll be doing the question now. Your rest of the doubts will be cleared. Okay. So write down the statement of the question. Verify that y1 is 1 and y2 is e raised to power minus x are two linearly independent solutions of y double dash plus y dash is equal to 0, and then find the general solution of the differential equation, given differential equation, satisfying y2 is 0, y dash 2 is e raised to power minus 2, and then find the, you write a word, then find the solution satisfying this. So obviously, let me just break it into steps, what you are supposed to do. So you are given two solutions. The first thing you need to verify they are linearly independent solutions. So linearly independent solutions further splits up into two steps. So the step number one will be you verify their solutions. How you are going to verify their solutions? By putting into the differential equation. Once you verify their solutions, your step number one is done. What is the second step? You need to verify they are linearly independent. And how to check linearly independent? Using the Wronskian. So once you confirm they are linearly independent, then comes a third step. They are asking you to find a solution satisfying this. So this particular solution which will be satisfying these two initial conditions. What conditions are these? Are initial conditions. That will also be a particular solution. But to find that particular solution, firstly we need to find the general solution, and then we will use these conditions to determine the values of arbitrary constants. So let's just do all steps one by one. It will be easier to see then. Right. So this is the equation y double dash plus y dash is 0. So y1 is 1. So how to verify this is a solution? Just compute its derivative. y1 dash is 0 and y1 double dash is also 0 because it's constant. So clearly y1 double dash plus y1 dash is 0. You can say 0 plus 0 is 0. So therefore verified that y1 is a solution of 1. So I'm calling this equation number 1. Similarly, we are going to verify about y2. y2 is e raised to power minus x. Its first derivative is minus e raised to power minus x. Its second order derivative is again e raised to power minus x. So if you add the first order and second order derivative, that turns out to be 0, right? And that is our differential equation. This is our differential equation. So clearly y2 is also a solution of the given differential equation. So we got their solutions. Now we need to check their li, right? How to check li? You compute the Wronskian of y1 and y2. So what was the formula of Wronskian? It is the determinant of a 2 by 2 matrix because you are having two functions. The first row is the functions itself and the second row is their first order derivatives. So what is y1? 1. y2 is e raised to power minus x. Their first order derivatives, y1's first order derivative is 0, you have already computed. y2 dash is minus e raised to power minus x. So you compute the value of this determinant. What does it turns out to be? Minus e raised to power minus x. And everybody knows this is always non-zero. Exponential function never takes the 0 value, right? So it's non-zero. It's never going to be 0. So although you can say in this particular question, no particular interval was given to us because these are always defined, right? We were not given the interval kind of things. So the interval, wherever it is given, only then you have to check the validity over a particular interval. But this one is free from the interval because this is always non-zero. It really does not depend upon any value of x for it to be zero or non-zero. So the Wronskian is non-zero implies the functions y1 and y2 are linearly independent. Li, I'm writing in short. Okay, so we are done. They are Li solutions. And now we will use this result which I stated, that if y1 and y2 are two linearly independent solutions, then this is the general solution. So therefore y is equal to c1 y1 plus c2 y2. c1 is arbitrary constant. So c1 into 1 plus c2 into e raised to power minus x. So C1 plus C2 e raised to power minus x, this is the general solution of what? One equation, whatever was original differential equation. And now specifically you want to find the solution which satisfies these two conditions. So one by one we will put these conditions and find the value of arbitrary constants. So what are the conditions? Y2 is 0 and y dash 2 is e raised to power minus 2. So these are the conditions. Y2 is 0 and y dash 2 is e raised to power minus 2. So this is y now. This is y. So first condition is y2 is 0. This means when you put x equals to 2, y is 0. This is the value of x. Okay. So x is equal to 2, y is equal to 0 will give me 0 is equal to c1 plus c2 into e raised to power 0. I'm putting here. So this gives me c1 plus c2 is 0. This is one condition. And the second condition which we get, sorry, I did mistake. X, for x you have to put 2. So it is c2 e raised to power minus 2. Yeah. For y it is 0. For x you have to put 2. So e raised to power minus x, this gives me c1 plus c2 e raised to power minus 2 is equal to 0. And second condition is about y dash. So how you are going to find y dash now? From y. So from y you differentiate, you will find y dash. What is y dash? Minus c2 e raised to power minus x, because this will be 0 constant derivative and minus will come here. So this one is the y dash. So the condition is y dash at 2 is e raised to power minus 2. So you connect this with this one. So this is e raised to power minus 2 is minus c2 e raised to power minus 2. For x you have to put 2. For y you have to put e raised to power minus 2. So this gives me c2 is equal to minus 1. And you get the value of c2. So from the first condition, you put c2 is minus 1. You get c1 minus e raised to power minus 2 is 0. So C1 is e raised to power minus 2. So this is simple calculation. Here we are not using any particular concept of differential equation. It's simple. In the solution, you can put the initial conditions and determine the value of two arbitrary constants. So you get your C1 and C2. So this gives me my final answer. C1 is e raised to power minus 2. C2 is minus 1 e raised to power minus x. This is the solution which they were asking us to find. So I hope this is clear to everyone. With this example, we have seen the results. What are the results I stated? We have used all of them in this single example. So I hope it is clear. So if anybody has doubt, I'll take up the doubts at the end of the lecture. So let me move ahead with the next thing. So the next thing we are going to discuss is to find the solution. Now in this particular example, we were not doing anything to find the general solution. We were finding the general solution. You can put it in these words. We were finding the general solutions when we know two particular solutions, and obviously that too when they happen to be Li, because I explained you that it is of no use if you know two particular solutions but they are linearly dependent. You need to know two particular solutions which are linearly independent to construct the general solution. So now we'll move towards the condition where we do not know the two solutions, we just know one of them. So this is the kind of questions we are doing, that to find general solution of second order homogeneous differential equation if one of the solution is known. So you just know one solution, but you do not know the other. In that case, how to do? So there is a formula. So I will not do the proof of the formula. The proof is given in the book Simmons. You can find, it's not very hard proof. You can follow this up. So I'm just directly going to tell you what the formula we are going to use. So what type of equation we are considering? Obviously, need not mention the linear one, second order. And here we are again focusing on the homogeneous one. Our right hand side is still 0. So suppose this is the equation which is under consideration. So if y1x is a solution of 1, this equation, solution means whenever I'm just saying solution means particular solution, right? Then the other solution of 1 is y2x. It is vx times y1x, where vx is integral of 1 over y1x square e raised to power minus px dx dx. So this is the formula you have to remember, that if I know one solution y1, then the other solution y2 I can find by multiplication of y1 with another function vx. And how that vx is coming from? This is the formula for vx. Again, to tell you, we are not doing the proof, so I will not be able to explain how we are getting this. There's a mathematical proof for the same in the book. So for questions, we just directly use this one. Is the integral of 1 over y1 square e raised to power minus integral of px dx dx. So and this y1 and y2 are linearly independent, because obviously there is no point to construct another LD solution. LD though we can construct anytime, right? If I'll give you a solution e raised to power x, you can tell me any other solution which is linearly dependent. Like this one, here y1 and y2 are linearly dependent. So I can just multiply this with any scalar. I can construct infinitely many solutions. But there is no point of doing that because they will be LD. What we want to find a technique to construct another solution which happens to be linearly independent. So for that, this is the formula. So let's just do the question. Okay, once you get y1 and y2, and then we know the general solution will be c1 y1 plus c2 y2. That result is still valid. Okay, so let's do the question for the same. If y1 is e raised to power x is one solution of xy double dash minus 2x plus 1 y dash plus x plus 1 y is equal to 0, then find the general solution. So again, breaking it down into steps. To find the general solution, we need to have y2. So according to the above result which I just stated, y2 will be v times y1. V is not a constant, remember. V is another function. Vx is integral of 1 over y1 square e raised to power minus px dx dx. So y1 is here. All what we need to identify to compute Vx is Px. So from where Px is coming, you look back, Px is this function, the coefficient function of y dash. So first, whatever differential equation you are given, you have to express it in this form. Only then you will be correctly identifying Px. So our differential equation is not in that form. The coefficient of y double dash is not 1. So this is equivalent to y double dash minus 2x plus 1 by x y dash plus x plus 1 by x, y is 0. So now I can compare and I can find my Px is this one, including the negative sign, minus 2x plus 1 by x. So you put this value of Px over here and I will get that. What is y1 square? E raised to power 2x. And this is e raised to power minus integral. Px is again a minus 2x plus 1 by x dx. Overall it is dx because there is an integration to be done. E raised to power 2x. So what is minus minus plus ho jayega? and from here you will get e raised to power integral dx, because sorry, 2 dx, because x by x is going to be cancelled, and another is e raised to power integral 1 by x dx. There will be two terms, right? So one will be 2, other will be 1 by x. So you can do the calculation, it's not difficult. So this is e raised to power 2x into e raised to power log x dx. So this gets cancelled and you get integral of e raised to power log x. And what is e raised to power log x? Is just x. So what is integral of x? X square by 2. This is a function of x. Remember, no need to add here the constant of integration. This I explained with the previous case also, when one of the question was asked that whenever we are computing, this is a kind of the multiplying factor or the integrating factor. There, when you perform the integration, do not add in the arbitrary constants, because that will be automatically adjusted in the final solution. So even if you introduce here a constant, you will see it will be getting adjusted when you will be writing the final solution. So no need to do it here. So this is just Vx, x square by 2. So what is y2x? Is Vx times V1x. So x square by 2 into e raised to power x. That is my y1. So I got my y1 and y2. Therefore, the general solution is given by y is c1 y1 plus c2 y2. So c1 e raised to power x plus c2 x square by 2 e raised to power x. This is my general solution. And now if they particularly give you two conditions, so using those two conditions you can find the value of c1 and c2. Okay, yes, to agree to answer your question, Vx may constant. Why didn't we add the constant? I'll show you. If you add the constant over here, the constant of integration, so y2, what y2 is becoming? In that case, y2 will be x square by 2 plus c into e raised to power x. So that is x square plus 2, x square by 2 e raised to power x plus c into e raised to power x. This will be y2. So in general solution, there will be one more term added, c2, this one, into c into e raised to power x. But then you can see this and this are combined. If you combine this and this term, you will get c1 plus c times c2 into e raised to power x plus c2 x square by 2 into e raised to power x. This is another constant. Just call it c3, right? So still you can say the solution remains the same, which I wrote the original one. It just contains two arbitrary constants. It cannot have a third one. If you try to introduce a third one, it will be adjusted automatically. Okay, so that's why this we are not going to do. That's why no more term like this, and this is the solution. So I'm just explaining you, even if you introduce it by mistake, it will be automatically adjusted. So why to just increase your calculation? Okay, now this by theorem, the result which I stated, they are going to be Li. So now how you want to be sure now they are Li? So what you know, how to compute? So let me ask you who asked the question, Chaitanya. You asked the question, how do we know y1 and y2 are Li? So I will ask you now, how do we know? If I want to know whether they are Li or LD, what should we do? You can write your answer, right? So now I want to know that what are these y1 and y2. Yeah, so obviously we'll use the Wronskian. So theoretically for this result, you can compute a Wronskian and then show Li, but particularly in examples it is easy to check. So you can compute your Wronskian here of y1 and y2. What is y1? E raised to power x. Y2 is x square by 2 e raised to power x, and their derivatives. Here it is this, and what will be the derivative here? It will be x square by 2 into e raised to power x plus 2x by 2. So that is x into e raised to power x. So you just compute this determinant. It will be turning out to be non-zero. It's easy to check. Okay. So let me do one more question of the same kind. So you will see the same things again. So in this case, the differential equation given to me is this, y double dash plus y is 0, and one of the solution which is given to me is this sin x. So I need to find the other solution, and I then need to find the general solution. So for that, I am going to compute Vx. Vx is integral 1 over y1 square e raised to power minus integral px dx. So what is px? You compare with the standard homogeneous one. Px is the coefficient of y dash. So there is no y dash here. Okay, there is no y dash term. So px is actually 0. So this makes the things easy. So this is sine square x e raised to power 0 dx. Right? So that's just e raised to power 0 only. So that just vanishes. E raised to power 0 is 1. So this is integral of cosecant square x dx. What is the integral of cosecant square x? Minus cotangent x. This is my Vx. So my second solution V2x is Vx times y1x. Vx is minus cot x. Y1x is sin x given to you. So minus cos x is the answer, y1 and y2. So the general solution is c1 sin x plus c2 cos x. So this is minus cos x. So up plus c2 bhi likhoge. So then also it is fine because that negative is going to be adjusted in the sign. So whether you write c1 sin x minus c2 cos x or you write c1 sin x plus c2 cos x, it's one and the same thing because that negative has the potential to be adjusted in the this sign of constant. So this is my general solution. So yeah, so I constructed a poll here actually. Let me see whether you can answer this one. So this is for this particular question I did. So you can vote your answer, although you already know the answer because we have done it theory, but you can check it using Wronskian. The function sin x and cos x, whether they are Li or Ld, you compute the Wronskian, and if the Wronskian turns out to be 0, they are Ld, otherwise Li. Okay, 1 more minute for the answer. All of you can compute, do your calculations, and then answer this one. Yes, meanwhile, everybody is responding. Let me take the questions. Okay, yes, Uday, you asked instead of Wronskian, can we just, yes, yes, you can always do that. Wronskian is a general technique, I told you, because we'll see in future when we'll be doing the higher order differential equations, then we'll be having three solutions. So that's why we need to train you with the general technique that given three solutions, then the concept of that constant multiple does not exist. The constant of scalar multiple exists only for two functions. So Wronskian is a general technique, can be applied to two functions, three and any. But if it is just two, then you can always use the basic definition of the scalar multiple. That is perfectly fine. Yes, Aditya, you asked, isn't the integration Of 0c. Yeah, yes, actually I'll correct that. Let me just finish this poll first and then I'll make the correction, but that will not change the solution. You can check that, because e raised to power c is going to be just a constant, so that constant is going to be adjusted in this vx, the function of x, and the general solution. It will be absorbed, that constant will be absorbed in the arbitrary constant. I will correct that. Okay, so okay, I'm ending up the poll. So I'm rewriting the answer for you, that what was supposed to be asked. Okay, so these are the results you can see. So not much satisfactory. So I'll explain that again. So if you were supposed to check whether sine x and cos x, but before that, let me correct that, the correction, e raised to power 0. So the integral of here, you can say, is a constant. So if this constant you introduce, so that will be adjusted here. Okay, so that will be adjusted in this constant. So if you even consider this, so it will be adjusted. So ultimately the final answer is still going to be same, c1 sine x plus c2 cos x. Okay, so your functions are sine x, cos x, and your derivatives are sine x derivative is cos x derivative is minus sine x. So what is the answer you get? Minus sine square x, and this one is minus cos square x. So this is minus sine square x plus cos square x. Everybody knows the value is 1. Sine square x plus cos square x, it is 1 always, whatever is x, right? Those of you are asking me over an interval or where it should be valid. So just like the previous question, or when I gave you the example of LDLI, the Wronskian is having this value -1 always. There is no dependency on the value of x. So you will see, if that kind of thing is there, that Wronskian is having value depending upon the value of x, then that interval or that particular values of x will be mentioned in the question statement itself. If the question statement does not include any information on the interval or anything like that, it will be automatically, you will see the Wronskian is having a universal value. So it's always -1, which is non-zero, therefore linearly independent, right? Yeah. So yes, W should be 0 for LD, linear dependence. Aditya, to answer your question, W should be so identically 0 for linearly dependence. We want them to be linearly independent. I'll recall you the result of where I written this. If the Wronskian is non-zero, then they are linearly independent. If it is 0, then they are linearly dependent. If it is non-zero, then they are linearly independent. Just remember this. For the time being, I'll tell you, forget the word identically 0, because if you're getting confused on that identically, just forget it. Wherever it will be used, if it in some particular question, I will explain there. In general, you just remember it like this. You will be able to do the questions. 0 means LD, non-zero means LI. Right? So yeah, this was a slide of the Wronskian definition, which some of you were asking me to show in the beginning. So that's all for